Well, share my screen. Yeah, so hi everyone. Thanks for joining us today, as well as those who will be watching the session later on. Welcome to Multimodal Weekly. This is our weekly webinar series hosted by 12 Labs, which is an early stage startup focused on building multimodal foundation models, video understanding, and we've been focusing, on hosting this webinar on a weekly basis over the past year and a half or so. Here are some of the topics that we tend to cover on a weekly basis. Obviously, new research in multimodal AI and foundation models, like our company, we're super excited about trends and things that are happening in the space. And so we attempt to bring a lot of researchers to talk about their work. Besides that, we also in the past invite startup founders, developers, hackers, partners, right? Talk about the innovative application of multimodal in different verticals as a field, as well as like specific like video multimodal projects from our Discord community. And oftentimes we have tutorials and guides from our internal team members talk about how to use a platform and API. So recently, yeah, we have a bunch of researchers coming and talk about their relevant work. So you can see a couple of the topics that you that was presented in a series recently, right? Everything ranging from say video annotation to like problem with collecting data, specific benchmarking solution for multimodal LLM, like video segmentation, video super resolution, video question answering, video diffusion models, etc. So yeah, we try to cover a broad range of topics with like the best research for currently working in this space. For today's session, I'm super excited to have the two presenters today. So the first one is Tsung-Han, who's also go by Patrick, currently a PhD student at UC Berkeley. The title of his talk is See, Say, and Segment, Teaching Large Multimodal Models to Overcome False Premises. I think the work is called SESAME, right? And basically looking at using large multimodal models for segmentation tasks. So like very important computer vision tasks. And so we are excited to hear how Patrick come up with the solution and present it. And then the second speaker is Jiamian Wang, currently also a PhD student at RIT. And a fun fact, I actually also did my master at RIT. So, go Tigers. So he will talk about his research work called Text is Mass, modeling a stochastic embedding for text video retrieval. I think this is actually very relevant to our work at our labs, because we also have a solution for like video retrieval. So curious to hear how the research approach here look like and how it can improve different retrieval benchmark. Yeah, so that's about the speakers. And just a quick logistic note for the attendees: feel free to send your question on Zoom chat, and then we'll have a Q&A session after each speaker finish. So with that, I will stop sharing my screen, and yeah, I will let Patrick. Do you want to start sharing your screen?
Yeah, I like to share the screen. So I think let's get started.
Yep, go ahead.
Yeah. Can you still see the screen right now?
Yes, I can see it.
Yeah. So today I'm going to talk about our work, See, Say, and Segment, teaching LLM to overcome false premises. So let's get started. I think in 2024, this year, we have gone through the went from LLM to multimodal models. So the input will be text plus image, and then the output will be text plus potential some visual outputs like segmentation mask. So, but the thing is that after you fine-tune the large multimodals to do some visual task, we found some severe false premise issue in this kind of models. For example, if you want to ask the model to segment a bowl of pineapple in this image, but obviously there is no pineapple. But however, existing models still probably do their best they can do to guess the instance. However, in real life, we want the model to interact with human in this way. They can not only reject the false premises, but also correct that, or sometimes provide some informative suggestion to the human. So that's the goal of the work. And because none of the existing works have explored this kind of issue, so we propose a new problem setting called See, Say, and Segment, called SESAME for short. So in this new settings, for the questions and the image pair, we ask the model to first see is to check whether the object exists in the image, and then say, reject or optionally correct the false premises if that doesn't exist. And finally, if we do the further dialogue, or we can do other kind of conversation, multi-round conversation, the model should be able to segment the objects. So it should be I think it's a step forward. We want to push the boundary of existing models toward the truly AGI. So our intuition is to gracefully handle some false premises queries. I think it's very important in our real life examples and applications. So first of all, to enable this application, we need to create a benchmark dataset. We call it the FP-RefCOCO. So here's the original RefCOCO examples. We have image and segmentation mask. So originally, we have the true premise query, called it TEP. And then we use the LLM methods to augment the false premise queries using the original true premise query. And then the model should be able to learn from a pair of true and false premises to learn how to correct that false premises. So that is the intuition and also the benchmark we want to evaluate the model. So here's the detail on how we created dataset and compare with existing non-LM augmented datasets. So basically, we just prompt the model using GPT 3.5 to generate some more reasonable false premises compared to existing one. They just randomly sample a category from the COCO, but sometimes it's not realistic and it's very weird for the real world applications. So with this dataset, we propose a new method called SESAME. First of all, here's the baseline. We just train in multiple large multimodals like Lava to do see and say, and then another model called Lisa to do the segmentation model. Yeah. And another thing is that we want to train the models end-to-end using our false premise correction datasets, existing reference segmentation data, and also some normal VQA data to train our final model called SESAME. So with this dataset and with our trained model SESAME, we can evaluate this kind of methods systematically. So here's the evaluation protocol. We evaluate on See, Say, and Segment respectively. So here's the results. For the SESAME model, I mean, the model trained end-to-end with all the data, we achieved the best See, Say, and Segment performance on various reference segmentation tasks. And yeah, we have 31% performance gain compared with Lisa, and also this one have 55 and 67% on See and Say. So most importantly, as you can see that the Lisa model, which is a great work to do the reasoning segmentation, although they're very great, but they suffer from forgot how to see and say after the fine-tuning. So that's their problem. So also we can do on-par performance on other natural segmentation tasks without false premises query. So here are some qualitative results. As you can see, for some kind of question like segment a lion, our model can identify that there is no lion, but the giraffe is noticeable. And also some irrelevant objects, like, for example, if we query the bicycle in the natural setting, we would probably only say that no bicycle is visible because the model didn't see some relevant objects in the image that need to be correct. And also, it can be extended to more nuanced or complicated settings where the model can correct like analogous concepts or related activities. So this is the very interesting example I want to show. So first of all, given this image, we can probably query like, please find me the plate on the table if available, and if not, locate where the ball is. So in the prior work, they will always or only do the segmentation as the best they can. But in that in the real world life, we want the model like our SESAME can say, sure, the ball is present and show the segmentation mask. And the second one is like do some conditional segmentation, and our model can also do pretty well. Like they can identify the onion and they know there is no lettuce. So the final one, if we only do the QA questions, the existing model fail, and our methods won't deliver the visual outputs, but do very well on existing QA task. So here's our contribution. We propose a novel problem settings like CSAME and segment, and we propose a new benchmark data sets and have the best performance. So here's our website, and yeah, I probably want to check out some questions that people ask for.
Yeah, no question right for right now. Is it? That's pretty fast presentation.
Oh, really? Is that, I thought it's 15 minutes or something. Okay.
Yeah, no, it's good.
Yeah.
So
Actually, we have an extension of this work. I mean, the motivation is that we want the model to take multiple images or a collection of data as inputs. So a lot of times, the model cannot answer some irrelevant information like false premises. So I'm not sure if you have noticed, but there's a new benchmark data set called Visual Haystack from Berkeley. Yeah, that is our another work recently to tackle the real multi-image or large-scale multi-image visual question answering. Yeah.
I see.
So this is just a promotion.
Yeah, I think since we still have some time, would you mind sharing some more about that Visual Haystack data set? Any like links or any? Yeah, it's a quick go through would be great.
Yeah, I can go very quick. Sorry.
No worries.
We have a blog post. So the thing is that my screen sharing is paused. So okay, I think we can resume. Should I?
Yeah, go ahead.
Okay. How to hold on. Am I doing the share screen right now?
You are still sharing your slides.
This one?
Yeah.
Okay, so here's our latest work on the visual haystack benchmark. So
Oh
as
no, you still sharing your SESAME slide, I mean.
Oh really? Okay. What about this one?
Yep, I see it now.
Okay.
Looking
So
good.
yeah, here's the visual haystack. So existing benchmark like needle in a haystack challenge, we found there are some problematic things in the visual world because sometimes, for example, like Gemini, they just overlay the text on the image and they probably only focus on the text retrieval and reasoning rather than the visual retrieval and reasoning. So we create a new benchmark called Visual Haystack that is a realistic and visual-centric needle in haystack benchmark for large multi-models. As you can see that by replacing the text needle to the visual needles, existing model like GPT-4o and Gemini generally fails. And we also found three interesting takeaways from this kind of benchmark. First of all, these kind of methods struggle with visual distractors. When we place more and more images to the model inputs, the model just cannot retrieve the correct document or correct image we need to answer the questions. And secondly, we found that if there are multiple key images or frames the model should retrieve to answer the questions, and the model becomes much worse compared to only the single needle experiments. That's the second takeaway. And finally, and it's the most interesting one, is the pathology of something like loss in the middle pathology, which means because we put the needle image or frames into the haystack of the image. So sometimes we found that if we put the needle at different positions, the model would perform very differently. For example, like GPT-4o, they usually prefer to put the data at the first place or probably at the last place. So it's kind of lost in the middle, which people have already found in the NLP domains, but we are the first to figure out that in the visual world. So that's 3 takeaways. And we built a new baseline methods called Mirage. That is a visual RAG-based solutions to improve the visual haystack performance and do much better on general multi-image QA. Yeah, that's
very cool.
promotion of our recent work. Yes.
Yeah, it just maybe you can just go into the Q&A session right now, and for the audience, if you have any question, feel free to just
Yeah.
either raise your hand or put it on the chat. Yeah, maybe I can get started. So like, for example, can you go back to that Mirage?
Go back to where?
Just the Mirage brush-based solution that you just show us.
Oh, Mirage. Okay.
Yeah. So this is like your solution to.
Yeah, it's a RAG-based solution where we have multiple images as input, and then first of all we have a visual compressor to reduce the number of tokens per image. That way we can take much more image given the same context length. And then we have a retriever. Essentially, it's just a RAG-based method. So we co-train the retriever with the large multimodals, and we only during the inference time, only the reference related or relevant images will be passed to the final large language model. Yeah.
Yeah.
It's
I'm just curious. So where do you retrieve the images from? Where's the data sources that you retrieve from?
Retrieve from I think all kinds of images.
Like, is it like a fixed data sources that you retrieve the image from, or is it more like open data sets?
Yeah, open data sets. Build the data sets using, for example, like Lava instruction tuning data sets. So it should be pretty open, and yeah, open internet images.
Awesome.
Yes.
And this part about integrating relevant visual information. So you identify this relevant visual information using.
Sorry, what do you mean?
like the part about integrating relevant visual information from these images?
Oh, the thing is that because some of the data in our instruction tuning data set, some questions requires multi-image reasoning. So I think we use a data-driven approach, which we just collect high quality data to train the model to do. Yeah, and during the training, we'll pass multiple relevant images to the model.
Yeah. Yeah, so that Vicuna model, right? Just
and recently we just keep updating the model to Llama 3.1, 8 billion. So stay tuned, and we will release the code after we finish it.
Awesome. Yes, so you can just plug and play all the open source.
Yes.
Multimodal LLM that can accept image as input, right? And then
yes, multiple image as input, and yeah,
and
really the pioneering rack-based solutions for that.
Great.
Yes.
Is there any other question from the audience on SESAME or this visual haystack for Patrick?
Should I stop sharing? Because I don't know if I still have any questions about that, or
yeah, maybe you can go back to the SESAME architecture one more time.
What?
The SESAME slide. Can you go back to that slide one more time?
Hold on, I need to process it. SESAME. Okay, here.
Yeah, and you have a slide on the architecture, right? Can you show us? I think it's like 6 or 5 or 6. Yeah, no, that one, 7.
7. Okay.
Yeah, so this is really interesting right here. So you have separate.
Yeah, I mean, first of all, we just try a very easy approach, which is a non-training approach. We just train using multiple LLMs to work together, like training multiple large multimodals. And we found that it sometimes is suboptimal So we want to train a holistic model. We call it SESAME. And the model is pretty similar to existing approach we just showed earlier. I can show you the model architecture is something like this one. Sorry. The architecture is very similar to this one. We just take the input and we will use a clip or other visual encoder to encode that to the features. And this line is for text output, and this line is for the visual output. So in fact, it's just a large multimodal plus the SAM.
Plus SAM, I see. So
Yes.
this, I assume this is SAM 1, right? Not SAM 2.
SAM 1, yeah, because it's
For image.
Yes.
For image. Yeah. Got it. Yeah, I think this is like very understandable. You set this base visual encoder, and you just plug in the segmentation mask, right? Using that base model. Yep. How was that training process? Is that like extensive?
Oh no, this training is very fast because we only do instruction fine tuning, which we only probably takes 1 or 2 days, less than, using only 2 A100 GPUs.
Yeah. Nice.
I mean, compared with, for example, Meta or Google, like OpenAI, their models, there's only 7 billion and it can be trained very fast. And if you have, for example, 8 A100 GPUs, I believe you can train the model within 1 day or even 12 hours. Yeah, should be something very reasonable.
Nice. I'm just curious, maybe this is like a high-level question, but like since you've been playing around with different open source large multimodal models,
Yes.
Is Lava still the best option, or do you think there might be other contender?
The thing is that although Lava is not the state of the art in terms of performance, but they are the pioneering work and they still maintain a code base, so it's easy to use, easy to play with, and some other subsequent work also use that code base. But if you are going to use the code base, I would recommend the repo called Prismatic VLM.
Okay. Yeah, maybe we can put that on the chat later on. So
okay,
interested
I'll put that on the chat later. But yeah, that is a work called Prismatic VLM, and their code base is very clean, and they also do the systematic approach evaluation on what some insights of training or something like that. I would highly recommend this paper and also their code base.
Awesome.
Yes.
All right. I think we're at the top of the hour. So thanks a lot, Patrick, for spending the time walking through your presentation and presenting work. If you have any question for Patrick, feel free just like put on the chat and you can answer asynchronously. So with that, I will unmute Jiamian, and then you can go ahead with your talk.
Yes, let me share my screen. Can you see?
Yes.
Hi, everyone. I'm here to introduce our recent work in multimodal learning. Specifically, it's about text-video retrieval, which is text-based modeling as stochastic embedding for text-video retrieval. So firstly, a little bit information about myself. As James introduced before, I'm currently a PhD student at Rochester Institute of Technology. My research mainly focuses on explore and exploit uncertainty on the quantification in diverse tasks, such as for high-level visual tasks. I'm currently focusing on text-video retrieval, and my research also covers mid-level research, such as personalized image generation using the diffusion model. And before ChatGPT dominated the world, I focused on more classic topics in computational imaging and also the image restoration. And currently, I focus on uncertainty quantification in 2 models, which is diffusion model and visual autoregressive model. So first, let me introduce some background knowledge about text-video retrieval. It specifically includes 2 specific tasks. One is text-to-video retrieval, which is given a text query, we want to find the most relevant video from the video pool. And the other one is video to text retrieval, which is given a video query, we want to find the most relevant text. And the first one is the focus of existing works. So the basic practice of text video retrieval is we firstly using some sort of multimodal to map the video and text into a joint embedding space, and then we perform retrieval. And here's some knowledge about that text video data. For video, we refers to the long or short video clips. For the text, it can come with different forms, such as caption, title, hashtag, and etc. So on the right, I give an example of text-video pair. For the loss function, to train such a retrieval model, one prevalent one is symmetric cross-entropy, which is basically it does pull the relevant pairs together and push the irrelevant pairs away. As you can see the sketch on the right. And here I provide the mathematical formation of this symmetric cross-entropy here. And in this work, we still adopt the format of this symmetric cross-entropy. For the evaluation matrix, we mainly adopt some several metrics, such as recall at K and median rank and mean rank. So the recall at K is a higher is better. For the other two, the lower is better. And before diving into our method, I would like to firstly introduce the key challenges in the related research. Since in text video retrieval, the video generally comes with lots of details, such as color, content, and motion, etc. So existing works mainly focus on how to design a powerful video encoder. And I roughly divide them into three groups. The first one is they can do text video interaction to perform a better video feature extraction. And the second type is we can perform a fine-grained video feature extracting, such as we do not feed the whole video into the frame into the video encoder, but we feed each frame into the encoder, and we find more fine-grained racial representations in the embedding space. And the third one is that we can adopt to additional information from other modalities to help better extract the video representation, such as the audio. But the common thing here is that in existing works, text and videos are generally mapped as vectors in the joint embedding space. For example, here, if you use a small clip model, they generally feed the video into the image encoder and do some fusion and get a video vector of 512 dimensions, and similarly, also a 512 dimension for the text embedding, and then perform retrieval in joint embedding space. However, we find that since video contains redundant details, and this means the text in general is really hard to fully describe the whole information in the video. So on the right, I give you an example. As you can see here, there's a relevant video text pair. The text description is a parrot man tries to lift a battery, which is the word while on a boat. And as you can see, there's a lot of visual details that is missing in this text description, such as whether the lighter is lightless or not, what is the emotion of this man, and where he stands, etc. So this naturally raises a question that, can we make text features more flexible and more resilient in the embedding space so that it can better capture the video representation in the joint embedding space? And here comes our method, which is called TMath, which is text is modeled as a stochastic embedding. So here you can compare between these two subfigures that in existing works, we map the text and the video into vectors in the joint embedding space, and we perform retrieval. The difference is that in our method, we define a text distribution as we call text mass, and we bridge this text mass with this text video in the joint embedding space. And actually, this can be easily implemented by a reparameterization trick, and I will introduce more detail later. And we call this as a stochastic text embedding. So here is a quick overview of our proposed method framework. So basically, you are given a text query, such as women are modeling clothes, and a series of video candidates from the video pool. and you put the video into the video encoder and put text into the text encoder. And our goal is to get a final single text, stochastic text representation and a video representation. And we perform retrieval in this strong embedding space. And I will introduce them part by part. So firstly, we do not make much modifications on the video side. For the video representation obtaining, we just adopted the well-established designs. So basically, we adopted the pre-trained clip image encoder to accept frames and get the frame representations. And then we perform some sort of feature fusion module to extract the final single video vector in the joint embedding space. For example, we can do a cross attention to compute upon the inputs of frame embeddings and the text embedding to get more meaningful or informative video representation vector. And our key design is about the text side, which is we want to develop a text mass. And in this case, the text is no longer represented as a point in the joint embedding space, but it becomes a distribution. And it correspondingly, it no longer corresponding to a specific semantics, but it covers a semantics range, and which is more resilient and more flexible. And as I introduced before, we can do it by just adopt the simple reparameterization trick. And here we get a TS. And epsilon here corresponding to the noise sampled from the normal distribution. And as you can see here, the key here is how we define this radiance function to make it work in our proposed method. And we find that the design of the radiance, the radiance is actually hard to be manually determined for different radiance, because firstly, the scale, because the radiance, it has a high dimensionality. The scale in each dimension can be different. And also the scale of the radiance module for each input text should be different. And also even for the same text, the scale for different video of the radiance should be different. And bearing all of these findings, we intuitively firstly design a radiance module by referring to the similarity between the text and video representation in the joint embedding space, which is we firstly compute the text frame similarities, cosine similarity values, and we define a radiance based on these scalars. And later on, we want to make it more flexible to make it a learnable module. That a simplest implementation is that we can add a learnable scalar onto this mathematical form. And here comes our second design of the radiance module. And a more straightforward extension of that is we can empower the radiance module by exchange the learnable scalar into a learnable linear layer. And here comes our final definition of this radiance module. And exponential function here is to make sure that the radiance values are always positive. So let's talk about the loss function. As I introduced before, we still adopt the form of the symmetric cross entropy. But in our case, since we have the stochastic text representation and text embedding in the joint embedding space, we just exchange the original text embedding with our proposed stochastic text embedding in this symmetric cross entropy. In each training iteration, we will just randomly sample the stochastic text embedding and to compute the loss. And since the text distribution is highly flexible, we want to find another, define more tools or like the module regularization to help us to better control the scale and the location of the text distribution to make it more effective. And here we introduce another term that we identify a very special point called support text vector. As I plot here, this support text vector is always located along the direction from the text embedding to the video embedding. And it will also always located along the surface of the whole text mass. So every time this embedding changes, the whole distribution, the scale and the location of the whole distribution will be changed accordingly. So similarly, we will put this support text vector into our symmetric cross entropy and form another regularization term to better control the text distribution. So in the end, we get a total loss that is the weighted sum of these two loss terms. So here's a quick summarization that during training, we will randomly sample the stochastic text embedding and put them into the loss function to do the training, to do the gradient descent. So during the evaluation, we also make some modifications to fit our text distribution. So given an input raw text, we will repeat the sampling for many times. And for each one, we will compute the similarity between the video embedding, and we choose the closest one as a final text representation for the metric computation. So let's have a look at the results. We compare our proposed method on several benchmark datasets. Here's two benchmark datasets on MSRVTT and LSMDC, and we compare under different model variations of 32 version and 16 version. And this table corresponding to the text-to-video retrieval results. As you can see, the proposed method can improve previous SOTA, especially on LSMDC a lot. And we also notice that there are some advanced methods that have the similar performance as our proposed method. And this, to clarify, this is because this specific method, they adopt much more additional data to train a foundation model. And here's more results on another two benchmark datasets of DiDeMo and VATEX. And you can compare between R1, R5, R10, MDR, and MNR. And here's another one, challenge text video multimodal dataset of Charades. So besides an encouraging text-to-video performance of proposed method, it also works well under the task of video-to-text retrieval, and you can refer to this table here. And we perform a series of ablation study. The first row here corresponding to the baseline backbone model that we are using. There's no stochasticity. And the last one corresponding to our proposed method. And you can clearly see the performance boost by each design. And we also discussed the impact of the radiance module. As I introduced before, we can simply compute the cosine similarities and use this one as an unlearnable radiance module design. And we can also adopt the learnable scalar and also linear layers. And we find three interesting observations is that as long as we use text mass in our proposed method, it can result in a performance boost compared with the baseline. And also, the radiance module is relatively insensitive to different implementations once you compare between this, the latter three lines. And the other one is linear performance best because it has the most learnable parameter amounts. And here we also perform some interesting radiance visualization. We want to see whether how the radiance looks like in the embedding space. For example, 512. And as you can see here, given a query weaving and modeling clauses and several example videos candidates, we find that if we compute the L1 norm of the radiance, we find that the radiance of the relevant text and video pairs is smallest. And actually, this is not by accident. To explore that point, we study the evolution of the radiance during the learning process. So as I shown by two examples here, for each figure, the x-axis corresponding to the training procedure, like training epochs, and the y-axis corresponding to L1 norm of the radiance module. So each line here corresponding to a specific text video pair. Since we are doing 1,000 text video pairs, there's only one relevant pair, and all the other 99 pairs are irrelevant. And very interestingly, you can see that the radiance, the L1 norm of the radiance module, especially for the relevant pairs, is always smallest. And as I shown by these two figures here, and actually we provide much more similar results in our supplementary material, that this means the proposed method can learn a very specific and accurate text semantics, especially when the text and the video are relevant to each other. And here we do some more in-depth analysis of our proposed method by comparing our proposed stochastic text embedding with the original vanilla text embedding. So the blue region corresponding to the cosine similarity distribution for the irrelevant text and video pairs between the vanilla text embedding and video embedding. So the red region corresponding to our proposed stochastic text embedding versus video embedding. When you compare the maximum between them, you can see that the maximum cosine similarity of our proposed method is smaller than the vanilla one, which is desired for the relevant text and video pairs. And similarly, we also plot the loss function, loss values for the relevant text and video pairs by comparing the stochastic text embedding and the vanilla text embedding. And similarly, we find that our proposed method enables smaller loss values, which is more desired. And we also, since our method involves the sampling during the testing time, we also discuss the effect of the testing trials. And the first line corresponding to the baseline result that without sampling, without the text mask design, and we gradually enlarge the sampling times, then we find that the proposed method performance becomes stable when we perform sampling for around 20 times. And we also uncover some other phenomena, like that the proposed method is kind of robust to the number of frames selected. Also, some little discussion about the weighted sum when we compute the loss function. So here are some takeaway knowledge of this work, that in this work, we propose a stochastic modeling method for text video retrieval. And basically this idea can be naturally leveraged to other domains that related to the multimodal alignment. And we specifically developed a similarity-aware radiance module that to facilitate the text semantics learning. And our proposed method achieves a significant performance boost compared with existing method. So this is basically the whole story of our method. You can check out the paper, code, supplementary material, and even the poster by referring to our GitHub repo. Yeah. Let me know if you have any questions. And thank you.
All right. Yeah. Awesome. Thanks a lot, Jiamian. Thanks for like an extremely detailed and scientific walkthrough of all the ablation study, about the results, and very details. I guess like choice that you made throughout the design of the solution. Yeah. I mean, I have a couple of questions, but I would love to let the audience to chime in first. All right, there was a question on the chat. What was the inspiration behind using the mass modeling approach? How did you guys come to it? You see the chat?
This is a very good question that relates to the motivation of our proposed method. Basically, we want to, we are studying the representation form of the specific for the text representation. That previous one is deterministic, and we want to make it stochastic. And if you want to do it stochastic, you introduce stochasticity, and then naturally it becomes a distribution. And then personally, I think when you form a distribution, formulate as a distribution, it becomes more powerful, and there's more place to design. It can be more flexible. And if you let me go back to the motivation slide. Oh, sorry. So specific to this task, we just find that there's a information mismatch between the text and the video. That the video is always contains redundant information and text representation. If you form it as a single vector, it can never encompass all of the information in the video. So we want to empower the text representation. If you want to do it in the embedding space, a natural prompt is to like change this representation form from a single vector to enlarge it to become a distribution.
Awesome. I think in one of your previous slides, you also, yeah, there's I think a follow-up comment here from Kingston. That's remind him of stochastic optimization algorithms.
Mm-hmm.
Right. So if we're going to run this.
Yep.
I'm not very sure about the high-level similarities mean in your question. I'm not sure if I understand your question correctly. For text mass here, we just refer to the text distribution we defined, and we call it like text mass.
Okay.
This much.
Got it. Sweet.
And like, if you want to unit test this.
Yeah, I think you have let's see. You have a pretty cool slide on the variational autoencoders, right? I think that was pretty cool because I haven't seen that for a long time, right? Since we moved to Gen AI. Can you go back to that slide real quick? Just take a look at that one more time.
And then,
you mean which one?
The variational autoencoders slide. There was a slide when you choose the radius. The radius.
Oh, yeah.
Yeah, this one, autoencoding version base by Max Welling. Yeah, I think the previous slide, right? But the whole point I think is you want to sample it, like you would sample distribution in a way that like.
Oh, you mean the framework?
Yeah, this slide, text mass distribution. Not this one, but like the following. The next one. Yeah, this one right here.
Mm-hmm.
Like reparameterization, right? This is a trick from from variational autoencoder.
Yes.
Yep. And on the slide on support vector support text embedding, is that similar to like support vector machine, or is it like I'm totally off base there?
Yeah, this is a very good question. That we draw inspiration from the support vector machine. That is the reason why we call that specific embedding as support text vector. Yeah.
Yeah, very nice.
Yeah.
And just to recap here, like you said the purpose of the support text embedding is to align text embedding with the video embedding. Like get it closer. Oh, what's the role there?
Yeah, actually, since we are developing a text distribution in the joint embedding space, it can be very flexible, and we want to put more control signals to help us better regularize the text distribution. And one way we find is that we can identify a very special point in the joint embedding space here, which is support text vector, because the location of this vector is very special. It always located from the distribution to the text embedding to the video embedding, and it always by design is located on the surface of the whole text distribution. So every time if we can control this specific point, it will naturally affect the scale and location of the whole distribution.
Yeah, awesome. That's great to hear. And I think that the fact that you mentioned this is also work for video text retrieval. Well, it's pretty
Yes.
cool. Yeah. So like video query and text as the output, right?
Mm.
Yeah. Okay, there's more question here for Kingston. From an engineering perspective, not from an engineering non-research perspective, do you have any insights about how we can implement video text retrieval better? And this can go to either Patrick or Jiamian. I unmute both of you, so either of you can chime in.
Yeah, I feel like the video text retrieval can be a little bit nuanced because it depends on the context of the video and depends on what models can process long context video, something like that. I only have some insights on text to video or text to visual information, so this question would be better to Jiamian or some other guys to answer.
Yeah. From my perspective view, I would say firstly, I think there's still a large gap, like a large room to be improved for text video retrieval if you compare the performance of text video retrieval to text image retrieval. For text image retrieval, we can get R at one like 70–80%, but for the text video retrieval, the majority group of the works, they're still using like they're still achieve like 50–60%. I think one of the most straightforward and effective way to improve the performance of the text video retrieval is to adopt more advanced foundation models. If you change the foundation model to a more powerful one, you can directly see the performance boost. This is most straightforward strategy. The other one I can think is the remaining problem persists is to bridge the modality gap, because the modality gap between the text and the video is always pretty large, and it's a more challenged way, a more challenged perspective compared to the text image retrieval, because there's times axis in the video side, and this is main focus of existing works. And actually, we recently have a new work that adopted the diffusion process to perform the text video retrieval to improve, to get further improvement over our this work I introduced today. Yeah, it's also about how to bridge the modality gap. Yeah, I think this is the one of the key problem existing in the text video retrieval domain.
Yeah, I think that's a great answer. I briefly took a look at your website, by the way, Jim, and it looks like you're going to be presenting that paper in NeurIPS, right? December.
Yes.
That new
yes.
paper you just mentioned.
Yes.
Yeah, Pro Labs also have a good present there. So yeah, we'd love to connect with you and learn more about that research when it's published.
Yeah, sure.
And on a side note, I also saw that you have another paper coming up soon, right? But ECCV next week called SQ Lava. Could you mind sharing a little bit on that?
That work was I collaborate with my PhD peers, that he come up with the whole idea, and I provide some guidance in the details. The basic idea is that for existing, when you train like fine-tuning the lava, existing works mainly adopt the QA pairs, especially the text answers for the gradient descent. But what we propose is that the question itself is a very good resources that can contribute to the learning, that we can let the model not only to optimize our answer itself, but we can let the model to learn how to raise meaningful and even accurate questions during the learning process. And this is the whole idea of this work. Yeah, we let the question materials to engage more into the learning process. And we finally developed the way called like self-questioning Lava.
Yeah, the reason I'm asking is because I think there's some sort of overlapping with the first presenters, right? On Lava and the extension of the base of open source multimodal LLMs. Yeah, so exciting to see how the community is still improving upon that framework and making it more powerful for different use cases. Yep.
Mm-hmm.
All right. So yeah, thanks both the speakers. I think we're at the top of the hour. So very exciting and insightful presentation from both Patrick and Jiamian. Learn a lot on multimodal LLMs, of course, but also like specific nitty-gritty details that requires to like build a solution. Especially excited about that, reaching the modality gap that you mentioned towards the end there, because I think that's going to be the key to push multimodal research moving forward. Thanks to the attendees for attending, and the recording of this session will be available on YouTube probably within the next 4 or 5 weeks. So I'll be sure to share it with the presenters so you can share it with your friends and other colleagues. And if you guys going to NeurIPS or any future conferences, let me know, and we'd love to connect you with some other team members from Twilabs. All right. Bye, everyone.
Thank you.
Yeah, enjoy.
Bye.
Hope you had enjoy your weekend.
Thank you. Bye.